Yeah, this one. Hello? Oh, okay, that works. All right, let's get the session started on convex optimization and other optimization-related friends. Uh, yeah, so I guess the big question today in this optimization session was whether this room was going to be, on this hot day, whether this room was going to be well-conditioned or ill-conditioned. So, right now, thankfully, it's well-conditioned, but we'll see how it goes. First talk is by Jingzhao on nearest neighbor classifiers. Go ahead.
Thank you, Satin. So the first talk actually is not about optimization, and it's non-convex. But let's see. It's a learning problem. Okay. So in order to introduce this talk, I want to first explain what is fast and multi-phase rates in the title. Okay. So what I'm showing here is a very standard training curve. Okay. So the x-axis here is the number of samples used for training the model. And the y-axis here is the test error. And so here we show two experiments. So one on nearest neighbor, the other is for multi-layer perceptron. And what we observe here is very expected. So as we use more training sample, the test error gets smaller and smaller. Okay, but there are two interesting things. So first, so the rate is much faster than what theory shows. Okay, so I will explain that in more details. And second, so we see that this is a log-log plot. And the fact that there is a change in the slope means that the convergence rate changes in the exponent of the sample dependence. And so this is what I call multi-phase rates. Okay, so this is just a brief overview. And we will start by explaining why this behavior, which is very expected in practice, does not really fall in what we see in learning theory. So this talk is about learning theory, sorry. Okay, and so to do that, we will first very briefly introduce what we mean by pack learning. And so in pack learning, we are using the standard setup where instead of learning directly from the population distribution, we sample a data set S, and from this S, we learn a predictor F hat. So this is expected to be very close to the global optimal predictor F. And then we test it on the population distribution and see how it performs. Okay? And so the quantity that we care about in pack learning is called excess risk. So excess risk is basically the number of error we make with the learned predictor versus the optimal possible predictor. So this is the excess risk. Okay. And in standard statistical learning, so there are two types of rates. So one is called parametric rate. And one very canonical or famous example is VC dimension. So basically, parametric rate says if I have a limited function class, in the sense that the function class has finite number of parameters, for example, then we can have very fast convergence. So the convergence, the dependence on n is polynomial, and the exponent is either 1/2 or 1. So it does not depend on the dimension. So this is what we call parametric rate. And another type of rates in statistical learning is called non-parametric rates. So for these rates, the key difference is that on the exponent of n, there is a d dependence. So d here is the data dimension. And therefore, in order to achieve constant error rates, so we would suffer from curse of dimension, which means we need exponentially many samples in dimension in order to learn a non-trivial function. Okay, so these are the two typical type of rates we get from statistical learning. And we will briefly overview what we know for nearest neighbor classifiers before this work. So here, sorry, this is a little bit dense on notations, but basically, so the only thing one need to note is eta. So eta, you can think about it as the ground truth function. It is saying, okay, so given an input x, what is the distribution of its label? Okay, and then there are two types of conditions. One is smoothness, says eta doesn't change too fast. And the other is margin, which says, okay, so eta has some nice property separating it from the 1/2 boundary. Okay, so these are the typical smooth and the margin in classifiers. So this is not particularly to k-nearest neighbors. Okay, and so prior to our work, so I think most of the known rates fall in this type of expression. And the thing that I want to highlight is that so alpha and beta usually are constants in order for the problem to be non-trivial. But in the end, we have a dimension d here in the exponent. So this means this rate will predict that we suffer from curse of dimension. Okay, so there is one exception, so which we learned from Daniel. So he mentioned that there was a paper in 1990 that also achieves parametric rate for nearest neighbor, so we didn't know this before. But it's in a slightly different setup. I think the message is similar. Okay. Okay, so up to now, this is what we know for nearest neighbor before. Okay, so what did we do in this work? Okay, so as we showed before, so we noticed that there are rich behaviors in practice versus what we know, which is only a worst case non-parametric rate. So for example, if I train a nearest neighbor classifier on a very simple classification problem, this is called normal logistic regression, where the data follows a normal distribution and the optimal decision boundary is a simple linear boundary. And here, we can see that as expected, if we train nearest neighbor classifier, the slope in the log-log plot are the same. So which means even though I increase the data dimension, the exponent in n does not change. So we are always benefiting from the parametric rate. Okay, so this is one thing. And this cannot be explained by previous analysis because here smoothness and the margin are all constant and d is increasing. Okay, and another, I think, more interesting thing is if we change the normal distribution into a distribution over a hypercube, and then we also have the optimal decision boundary to be linear, but we slightly rotate this decision boundary. Then we no longer benefit from this benign rates. Because if we look at the convergence rates, so here the slope is changing with respect to d. This suggests that even though we have a very simple decision boundary, k-nearest neighbor doesn't always achieve parametric rate. So this is the motivation of our work. We want to propose a condition and framework for understanding why this happens. Okay, so this is, as I said, the gap between theory and practice. One is why does parametric rate exist for non-parametric models? And second, why do we observe diverse convergence rates across different ranges of sample size n? Okay, so as we see here, so initially the rate is fast, and later the rates change and become slow. So I think the only intuition that one needs to take from this project is the reason behind this is very simple. So if we look at the FMNIST dataset, so it's a dataset with different types of clothes. And you can see that it is easy to tell the difference between like shirt and sneaker, but it's hard to tell between sneaker and ankle boot. Okay, so this means, so each data has a different level of difficulty for being learned. Okay, and if a data is easy to learn, then it results in a fast rate. And if a data is hard to learn, then it results in a slow rate. Okay, so this is takeaway. And this is also why we study, although this behavior happens for both nearest neighbor and neural network training, we can only analyze this for nearest neighbor because for nearest neighbor, we have an easy way to quantify this level of difficulty. And so here, if we consider a uniform distribution over a rectangle, so clearly the points near x are easy to learn and points near x prime are hard to learn. And the key quantifier is by looking at a radius r, a ball of radius r near x prime. And then we can see how much blue label are near x prime and how much red label are near x prime. And we can, so this plot will correspond to x, and this plot, the other plot will correspond to x prime. Okay, so I don't want to go into detail, too much details, but using this radial density distribution, we can quantify the learnability for a particular instance x. Okay, and so the main technical contribution for our work is proposing a framework for quantifying instance learnability. And using this framework, we can, in theory, prove that if I have a normal logistic regression, then nearest neighbor classifier can achieve the optimal parametric rate d over n, where d is that problem dimension, n is the sample size. And for this slightly rotated, very simple distribution, uniform distribution, linear boundary, nearest neighbor classifier will have two phase rates. It will be parametric first, and then suffer from curse of dimension later. And we also have a corresponding super polynomial lower bound to show that the second phase probably happened. It cannot be avoided. Okay? So basically, that's the end of the talk. So in summary, we provide a theoretical framework for for generating parametric rate and multi-phase rate in KN classifiers. So KN classifier is non-parametric. So previously, I think similar analysis didn't exist. Okay, so thank you.
We have time for a few questions. Okay, well, maybe I have one quick question from me. So this is very cool work, but how can you generalize it to other settings beyond logistic regression or like?
Oh, yeah, so I think it's very easy to generalize beyond logistic regression.
Okay.
What is hard is to generalize beyond the nearest neighbor.
And then never.
Yeah. So this definition applies to any function.
Okay.
Yeah.
I see. Okay. Any more? All right.
Okay.
Thank you. Let's stand a speaker again. Right. And the next talk is on maybe. Not quite sure if it's about oneness optimization either. It's about circuit lower bounds.
I didn't make the schedule.
Yeah. Let's see. Okay. Yeah, I think we wanna. Yeah, I mean, I think it's this one. I think. All right, and Daniel's gonna give a talk on it. Go ahead.
Yeah, thank you. So just to give a warning, this is even less about convex optimization. What it is about is, as you said, circuit complexity, both classical and quantum, and how it relates to learning theory. And I'll do my best to make this accessible. I know most of you are not quantum people. But you will need some understanding of circuit complexity, though, unfortunately. Okay. So a pretty fundamental problem in quantum and also like classical complexity is how many resources are needed to produce something. In the quantum case, we care about like how many resources do you need to produce a quantum state, but you can also think about this like how many gates do you need to compute a Boolean function or something like that. So yeah, Boolean function analog. The non-uniform version of this is just like how many gates do you need. But the uniform version of this is how much time do you need to find the circuit that prepares whatever resource you care about, whether it's a Boolean function or a quantum state. And this is the topic of this talk. So basically, to give a general idea of this, let's say you have a quantum state or maybe like a classical distribution. They're parameterized by like a natural number n, and how much time, given the number n, do you need to synthesize said quantum state or distribution. So that's like the fundamental problem that we're dealing with here. And sort of recently in quantum, we came up with these new kinds of complexity classes. They're basically like state synthesis versions. And you can think about them as having a classical input and a quantum output, whereas classical complexity is about classical inputs and classical outputs. And just to show that these things are meaningful, we were able to show things like state p space equals state QIP, which is like the fundamental analog of p space equals IP from classical complexity theory. And in general, how this relates to learning theory is we know that states or functions, Boolean functions that are harder to produce should also be harder to learn in general. So, but this is like general intuition. We obviously want to formalize these things. So as an example, something like a product state or a product distribution is easy to learn. Something like a random function, or in quantum, just we call it a Haar random state, it will be very hard to learn, just information theoretically. So yeah, can we formalize this connection? And actually, a classical version of this exists already. This is due to Fortnell-Clivens from Colt 2006, and there's been a line of work that has appeared in various different conferences that builds on this. So the takeaway of our result is that slightly non-trivial tomography algorithms, I'll go into what tomography means just line below, but algorithms for quantum states or quantum unitaries implied new results about quantum state synthesis, and in small parentheses, also about classical circuit complexity. And what I mean by this is, given copies of an arbitrary quantum state, you want to output a description of this quantum state that is close in trace distance. So this is like the analog of distribution learning, classically, where you would say be given samples from some distribution, and you want to output a description of this distribution that is close in total variational distance, or something like that. So yeah, it's like almost like a non-commutative version of this, if you're interested in these kinds of problems. And basically, what I mean by non-trivial is basically like similar to distribution learning. Any kind of like algorithm that works for this set of all distributions requires exponential samples. Not just exponential time, but exponential samples. There is also a way, a quirk to this quantum version where you can get away with a quasi-polynomial number of samples, but you'll actually just blow up your time complexity a lot. And basically what we say is that if you can achieve like just slightly under exponential sample complexity without blowing up your time complexity too much, this would already imply like very, very strong lower bounds for quantum state synthesis. I'll let you digest that a little bit. Basically, the normal sample complexity is 2 to the theta of n, so this is just slightly under linear in the exponent. Like I said, without blowing up your time complexity too much to, say, 2 to the quasi-poly. So as an example, this is like perhaps the most general quantum version of this. If you can prove non-trivial learning algorithms for this quantum analog of AC0, it would imply this set of circuit lower bounds for state synthesis. But I think perhaps more interesting to you guys in this audience, you actually prove things about classical circuit complexity and classical complexity theory. And basically this follows because of connections between these quantum analogs and their classical analogs. So for instance, E is just, you probably know about what exp is, which is things that run in 2 to the poly n. E is just a set of decision problems in 2 to the theta of n. And this would basically prove the first non-trivial lower bounds against TC0, which is basically, you know, if you're like Ryan Williams, that's your big goal. And I think a key part of our work is that this has no cryptographic assumptions. So we don't need things like the hardness of LWE for quantum or LPN or any of these kinds of things. It's a purely complexity theoretic argument. And so I think just to summarize the result, there's sort of an optimistic view or a pessimistic view of this. The optimistic view is that quantum learning can be a potential path to achieve breakthrough results in classical and quantum complexity theory. So not only are these circuit classes useful and interesting to learn in their own right, but they would also come with a bunch of other interesting results for other fields that I think you should be aware of. Unfortunately, the pessimistic viewpoint is that we probably cannot learn these things. This is similar to how we probably cannot learn TC0 classically because it contains things like learning parodies of noise and LWE. And I guess since I have time, how much time do I have left?
You have like 4 minutes.
4 minutes, okay. So basically, just to give a very, very brief idea of what the proof is, unfortunately it's more complexity theory than it is learning theory, but we sort of set up a win-win scenario. That's why we actually have one of two conditions in our results. The first is if we assume the following complexity theoretic result about p-space and sub-exponential time quantum computation, then we get the following result about BQ sub-exp and quantum circuits of bounded polynomial size. And this actually combines a bunch of different classical and quantum results. It's basically like a quantum circuit diagonalization theorem, or hierarchy theorem rather. And the state version follows. But perhaps more interestingly, if we assume the other direction, then what we can show is actually the first complexity theoretic pseudo-random unitary, which has the following parameters. Basically, it takes a really, really long time to compute, but is also secure against sub-exponential time adversaries. So it's a very, very strong PRU. And basically, the idea is that obviously, if you can learn a circuit class that contains this PRU, that means that it cannot, well, if you can learn a circuit class, it cannot compute PRUs. And if you cannot compute PRUs, then this breaks the assumption of this theorem. And that's how our results follow. And basically, we need new insights about low-depth pseudorandom unitaries, which basically has been done in conjunction with this currently unpublished work by Schuster, Huang, and I'm unfortunately forgetting two of the other authors, but you can ask me about that offline. Yeah, and so that's pretty much all I wanted to talk about, and thank you.
Questions? Plenty of time.
Thank you for the talk. Sorry I didn't follow everything, but so I have maybe a general question. So we know that learning circuit is hard for classical circuits. And so are there any benign cases in quantum where learning circuit can be solved, but not in its counterparts for classical circuits?
I mean, certainly, like, for instance, we know that we have, like, these quasi-polyhardness results for AC0 due to Kharitonov that are built on the quadratic residuosity, and those certainly break for quantum, right? Because quantum can do factoring and things like that. But I think there aren't actually results because it turns out there's another paper that like quantum you can embed LWE or a form of LWE in AC0 as well. So you still have, if you assume LWE, there's still results there. But it's certainly possible that you could build, none of the popular circuits, like I said, NC0, AC0 have this, but it's possible that maybe TC0, there might be some quantum algorithm where there's no classical result. But I don't know any off the top of my head currently.
Okay, so the lower bounds are broken, but there's no very well-known upper bounds.
Sorry, what do you mean by that? What lower bound is, like, the classical lower bound for AC0 does not work for quantum, but we came up with a new lower bound, basically, that does hold for quantum. That's what I'm trying to say.
Any other questions? Or maybe I'll ask a very quick question. So I was wondering, like, how far can you extend the learning requirements for your result? Because if you relax just tomography, approximate tomography to like, pretty good tomography, like if you have a set of measurements and you want to just output a state that is consistent with those measurements, you can do that in sub-exponential time.
Yeah.
We know how to do that in sub-exponential time.
Ultimately, like I said, our result relies on this like PRU construction. So ultimately, as long as you're able to distinguish it from Har-random, that's good enough. Okay. I'm not quite sure if you can use pretty good tomography or these kinds of things to distinguish from Har-random, but if ultimately you can get from that to distinguishing from Har-random, then all the results follow.
Okay. All right, cool. Well, let's thank the speaker. Next talk is, I believe, by Qingxiao again. And this is one of the papers which won a Best Student paper, so let's congratulate the authors on this paper again. I believe this is about convex optimization, or at least convex concave. So go ahead.
So hello again. So actually, so let's plan to come here to present the work, and he made the slides, but his visa got rejected, so I need to give this presentation. So this presentation is actually about convex optimization. So let's see. Okay. So we will start with the classical results. So in convex optimization, so we are usually minimizing a convex function f, and the goal we want to achieve is to find a point x such that it's epsilon close to the optimal point. Okay, so this is a standard setup. And so to review some classical results, so first we can run a projected gradient descent. And for smooth function, we can achieve 1 over epsilon convergence rate. So this is classical textbook results. And one phenomenal and famous result by Nestorov in 1983 is that so this rate can actually be accelerated to 1 over epsilon to 1/2. And this was shown also by Nestorov to be optimal in 1980s. Okay. So this is some background in convex optimization. And then let's see what happens for min-max problems. So we are considering a different problem, which is convex concave problem. And so here we have a function f that is convex in x and concave in y. And here, instead of finding the optimal point x, we want to find a set of points, x, y, such that this is something similar to the duality gap is bounded by epsilon. Okay. So which means that we optimize y versus optimize x, the bound can be bounded by epsilon. So this is a counterpart for suboptimality in minimization. And here we also know that we can run the straightforward generalization is gradient descent ascent, which we run descent in x and ascent on y. And here, so we know the rate is 1 over epsilon squared. And actually, many years ago in 1976, we know this is not the optimal algorithm. So we can run extra gradient descent. So extra gradient means instead of taking the gradient at the point where I want to update, I take the gradient by moving half of the step. So the place where I evaluate the gradient and the place where I update the parameter is different. Okay, so this is extra gradient method, and I think so. At least explicitly in 2019, this was proved to be optimal for convex concave smooth problems. Okay, so all these are first order problems, and we see that so Nestorov achieves optimal minimization algorithm, and extra gradient achieves optimal min-max optimization algorithm. Okay, and so let's look at what happens for higher order methods. So what I mean by higher order methods is instead, when we minimize a convex function f, instead of just getting feedback in gradients, we can also get Hessian or piece order derivative. Okay, so the gradient step can be thought of as minimizing a first order approximation in Taylor expansion when p equals 1. Okay, and so higher order methods, for example, by Nestorov and Polyak in 2006, says, okay, so instead of doing first order expansion, we can do second order expansion or piece order expansion. Okay, and if we have this oracle where we minimize this piece order expansion and do this gradient descent-like updates, so this is called actually cubic Newton step, then we can achieve faster rate. Okay, and this rate is actually epsilon to the negative p. Okay, so we can check when p equals 1, this is the rate of gradient descent. When p equals 2, this is the rate of cubic regularized Newton. Okay, so everything looks nice so far, and the interesting thing is, so for min-max optimization, okay, the story is slightly different. Okay, so again, so we can run tensor step. So the expression is a little bit hard, but it's a counterpart for the tensor step in minimization. We can run a tensor step for min-max optimization, and we can achieve a rate that is epsilon to negative 2 over p plus 1. Okay, but there is an open problem here. Okay, we will see why. Okay, so what we introduced is so for first order optimization, so everything is clear. We know when p equals 1, we know what the optimal algorithm is. Okay, but when p is larger, so we can see that if we run Nestorov's acceleration on tensor descent, we get this kind of rate, epsilon to negative 1 over p plus 1. Okay, this was once speculated to be optimal, but later by Monteiro and Sweater, they designed a very clever trick. We call it MS acceleration in our work. And they can combine Nestorov's acceleration and extra gradient descent to achieve faster rate for minimization. Okay, this is very interesting because extra gradient was only known to be useful for min-max problem. But somehow they use this technique to further speed up minimization problems. And so this rate was known in 2013, and it was eventually proved to be optimal in 2017. Okay, but then the question is, can we use similar combination to get faster rate for min-max problems? And but ever since 2013, there is no progress in deriving a faster rate for min-max problems with p-solder oracle. And this was actually conjectured to be optimal in several work, for example, by Lin and by Nesroff. So their lower bound is a restricted lower bound, where they either restrict the problem class or restrict the algorithm class. So in some special setup, this is the optimal rate. Okay, so this was suspected to be optimal. And so our work is basically to understand, we start by thinking, so is this truly optimal for the general case where we care about? And in the end, so this paper, we show that previously it was not optimal. And the takeaway is, so instead of going from natural acceleration and extra gradient directly, we need to use technique from MS acceleration and extra gradient descent. And if we combine them cleverly, then we can get faster rates. Okay, so this is the rates we get in this paper. But still, so the lower bound is missing, so we don't know whether this rate is optimal. Okay. So this is just the high-level takeaway from our paper, and so what is the main contribution of our work. And so the algorithm is actually very complicated, so there's no simple explanation, but I will just give a high-level intuition of what we are doing. Okay, so we are using, so we are using something that is like a catalyst. Okay, so if you know catalyst from finite sum optimization, so basically instead of solving the original problem, we add a regularizer such that the problem becomes smoother. Okay, so we have a triple loop, and that is because we first add a regularizer to the variable x, which is the minimization variable, and we can solve this using a proximal oracle. And in order to implement the proximal oracle efficiently, we need to add another regularizer on the maximizing variable y. Okay, and in order to solve this proximal oracle for this problem 3, we can run standard NPE, Newton proximal extra gradient. And this part is fast because after regularizing twice, the problem will become well conditioned in the sense of uniform convexity. Okay, and therefore, so the inner step, the step 3, takes only constant number of steps, but the middle and the first step will take epsilon to the -2/7 iterations. Okay, so if you look at this, so basically we apply this rate twice for both outer and the middle loop, and the inner loop takes only constant number of iterations, and therefore the total complexity is simply doubling this, which is epsilon to -4 divided by 3p plus 1. Okay, so that's the high-level idea of our algorithm. And I just want to briefly summarize so what I'm talking about. So basically, so this work is we improved a complexity upper bound. We provide a complexity upper bound for a second-order convex concave problem. So the previous rate was long conjectured to be optimal, but we show that it's actually not. And another thing I want to highlight is although many complexity bounds are already known to be optimal for minimization problems, but for convex concave problem, there are a lot of open gaps. Okay, and that's it. Thank you for your attention.
Very nice. Any questions?
Do you believe these improved rates could hold for more general variational inequalities?
Yeah, actually, so for general variational inequality, it holds, as long as the smoothness condition holds. Yeah.
So do you need some monotonicity also for the variation?
Yeah, for monotone variational inequalities.
All right. Any other questions? All right. Sounds like we don't have any more. Thank you so much.
Okay, thank you.
Next talk, I'm pretty confident, is on complex optimization, and it's on accelerating gradient descent with silver step sizes. Jenna will be giving the talk. Let's see.
All right, thank you. Go for it.
Yeah, well, thanks everyone for being here. This talk will be about a new and exciting way of accelerating proximal gradient descent. I'm Jinho from University of Pennsylvania, and this is a joint work with Jason, who is also at Penn. So let me start with, as a background, let me start with the simplest textbook setting, which is just minimizing a smooth and convex function f. So the very first thing we learn in convex optimization class is how fast those first-order methods converge. In particular, how they scale with the number of iterations. So we know that, we learned that a gradient descent has this 1 over t rate, and if you add momentum, it can be accelerated into 1 over t squared. And some people ask whether this momentum is actually necessary for acceleration. In other words, can we just accelerate only by changing the step sizes? So why one should care about this problem? First, because there's a conference in learning theory, maybe it is fair to say that this is an interesting theoretical question on its own in terms of trying to understand what is and pushing the boundary of this algorithm. And furthermore, there are more empirics-focused works which uses time-varying step sizes, which are shown to be effective for accelerating a neural network training or solving parametric problems. So just as a maybe 10-second summary of the old history, in the 50s, this was shown to be true, but you additionally need to assume that f is quadratics. This is a classical result by Young in the 50s. And people sort of recently revisited this problem, but in terms of the rate, these essentially give you only an acceleration by a constant factor. So in this recent work by Ultralo and Perillo, they introduced this sequence of step size called silver step size. So for here, we assume that the length is power of 2 minus 1. And I didn't really even write the precise definition of this step size. What I would just say is that this is based on the power of some value called silver ratio, which is actually just a number, 1 plus square root 2. And instead, I draw a plot here, which shows a lot of interesting patterns. So as you can see, the step size is non-monotone, and it has this fractal-like pattern, which comes from the fact that this can be also recursively defined. And finally, sometimes this uses a very large step size. For example, this step in the middle is actually has size polynomial in t compared to constant, which is very large. So remarkably, what they show is that this actually allows you to accelerate gradient descent. And the rate might seem as weird because the exponent reads as a log base to 1 plus square root 2, which is roughly 1.27. So this shows that you can actually at least partially accelerate gradient descent just by using step sizes. So just for the last couple of years, there has been many interesting work in terms of trying to understand this work. There will actually be another talk on this topic later in this session. And an interesting part is that somehow the fastest rate that people achieve is still this weird-looking 1.27, and this is actually conjectured to be optimal. So that has been the background, and let me move on to our work by starting with a simple and fundamental question. So we know that GD, even in theory, extends to many different settings, but all the recent works on step size acceleration assume that the function is smooth and convex. So it is very natural to ask whether the step size acceleration can be extended. And there are some challenges, or I would say nuances for this problem. First, one might think that this problem is sort of trivial, it just naturally extends. But that is not always the case. So for example, in this classical Young step size, even very simple extensions from quadratic, you can show that it actually provably doesn't work or say even converge. And second, I didn't really mention how the silver step size is exactly defined, but its derivation is very much dependent on the fact that the function is smooth and convex. That means that if I were to switch to a different setting, I may need to search for new step sizes. And this is a difficult problem, essentially because this is not convex, and all I can essentially do is just some kind of grid search. And finally, I'll explain this part later, but the analysis is rather non-standard and complicated. In part, the key idea and challenge is that for acceleration, you need this very large long step. And this long step might be by itself pretty bad because it may overshoot on the objective. So what you need to show is that when combined with shorter steps, it is actually helpful. So in other words, you need to very carefully keep track of how this large step affects all the other iterators, essentially. So the setting that we consider is what's called composite optimization. So instead of just minimizing f, we minimize f plus h. And the standard assumption on h is that it is convex, and it can be non-smooth. And we also assume that its proximal operator can be accessed. So it is an easy way to think of h as some kind of regularization, such as L1 norm. So an analog of GD here is a proximal GD. And of course, this includes vanilla GD, but also projected GD, ISTA, and so on. So as I kind of already had explored in the title, as a main result, we show that proximal GD with silver step size accelerates, and we also achieve the same asymptotic rate. And this is basically the first result beyond the simplest setting. And I would also like to remark that the appealing part of this result is that we used the same step size, so there was no need to search for new step sizes. So for the rest of the time, I will try to provide some high-level ideas of our analysis. And again, this analysis is already pretty complicated, even if you only have a single function. And in particular, in our setting, we also have this additional h function. So in order to avoid this complexity, what we try to do here is borrow certain parts of the analysis as much as possible from what we know for vanilla GD with step size, which corresponds to proximal GD with h being 0, and also proximal point method, which is proximal GD when f is 0. So just as an overview of how these sort of analysis works when it is vanilla GD for silver step sizes, basically showing rate is equivalent to showing that this value is non-negative. So what we do is, there are some valid inequalities that we know to be true with respect to each pairs of iterates and their first order information. So I wrote that as a Qij being non-negative. And basically the key challenge is to show that the left-hand side is equal to the right-hand side, because that will just automatically tell me that the left-hand side is non-negative. And unfortunately, sometimes it's not enough to, just for this to, get the equality. So I also need to, obtain some sum of squares. So this high-level template is basically the same for our setting for proximal GD. But now instead, we have pairs of valid inequalities for each iterate, because now we have each for f and h. So we need to characterize those coefficients, each for f and h, and also the sum of squares. So again, I need to characterize this complicated sum. So what I do is, instead of trying to do this from scratch, I try to use as much as possible what I know from this setting. So how we start is that we basically use the same coefficients for f for all I and j. So this is very natural, and it is actually a good starting point. But the issue is that, this doesn't just directly immediately solve our problem. In particular, the inequalities, these Qij and the Qfij, are not the same. And that is because, essentially, we moved on from just GD to proximal GD. So this induces many extra terms that I need to take care of. And we show that once you carefully define this coefficients for h, you can offset these terms. So this is a good news, but still we have some extra terms. So the final piece is to show that these remaining terms are actually a sum of squares, so that still everything is non-negative. At the end, this boils down to showing that some high-rank matrix is positive semi-definite. And what we show is that after some simple operation, this matrix is Laplacian, which proves that. And an interesting part here is that this Laplacian structure matrix sort of appeared in the analysis of proximal point method, and that is what I mean by borrowing proof also from the proximal point method. And yeah, all this can be done with constant factor override in the rate. And so far, I only mentioned that these coefficients are complicated, so I guess I'll illustrate with few words and pictures in terms of how these work. So basically, these are defined in a recursive way. So I will try to illustrate how these coefficients look when the length is 2t plus 1, based on the length of t. So it turns out that roughly the first and second half of the silver step size for 2t plus 1 is exactly silver step size for length t. So I can sort of use the coefficients that I know to fill in the blanks here. But I still also have this very large step in the middle. And again, I need to control how this affects all the other iterates. So I add those correction terms. So these lambdas are essentially defined in a recursive way by using those recursion and doing some correction. So as a summary, we show that proximal GD accelerates with silver step size with same asymptotic rate. And I would like to also mention that what we did at a higher level is that we have some algorithm for the unconstrained setting, and we use that to design and analyze a new algorithm in the composite setting. So we recently developed like a general framework in terms of doing this for certain first order methods, and that in particular simplifies and extends the analysis here. This just became available on arXiv, I think, yesterday, so you can also check this preprint if you're interested. So that will be the end of my talk, and thanks for your attention.
Any questions?
Thank you for an interesting talk. Just wondering if the function is strongly convex, is there any similar improvement here?
Yeah, so for strong convexity, then the iteration complexity, is like the acceleration is shown in the, dependent on the condition number. So yeah, that just naturally extends for the strongly convex setting. So I guess the dependence on kappa becomes like kappa to the 1 over 1.27.
Okay, thank you.
Oh, sorry.
All right, let's thank the speaker again. And yeah, the next talk. Sorry. All right, the next talk has convex optimization in its title, so I'm pretty sure it is about convex optimization. This one? Yeah. Oops. How do you... I think we need some help here. Oh, no. Okay, here we go. All right. David Martinez-Rubio is going to give the talk.
All right, thank you. I'm going to talk about minimization in high-order smoothness. We'll also talk about Monteiro-Spider acceleration, as we heard about 2 talks ago. So this is joint work with my collaborators, Juan Pablo Contreras and Cristobal Guzman. For many problems that we care about, we have naturally regularity with respect to non-Euclidean norms. Like some examples are box simplest games, where we have naturally this regularity with respect to L infinity and L1 norm. Also, LP regression, of course, has regularity with respect to the P norm, or logistic regression has constant Lipschitz gradients with respect to the P norm if the data lives in a constant radius p-ball. And there are many, many other examples you can come up with. So in this work, we're interested about solving the convex problems that satisfy that some high-order derivative is Holder continuous, but with respect to an arbitrary norm. So in particular, this first condition over there is going to imply that the gradient of our function at some point y is close to the first order, so the qth order Taylor approximation at some point x by an amount that depends on the distance between x and y. And this is relevant because the algorithms are going to exploit that we can call an oracle that returns the first q derivatives of our function, construct this Taylor expansion, and then optimize that, or a regularized version of that, in order to optimize f. We also optimize other structure functions, particularly in the limit when q goes to infinity. The second inequality would mean essentially that our model is the whole function, but only in a ball of specific radius. And that gives us the ball optimization oracles that have been used quite successfully in the past, but only in the Euclidean case. Our results work for any norm, but we have also lower bounds that match for p norms. So in particular, we get accelerated and accelerated algorithms, and also algorithms for a ball oracle that use an inexact proximal point algorithm. So some of these results were already known when q plus 1 is greater than p. So here I only included a case where we have Lipschitzness of the q derivative instead of Hölder continuity, just to simplify things. But we solved this in a more general way, even in that case as well, since we can work with inexact proximal point oracles in full generality. So as it happens, and it was known for the first order case, when p is equal to infinity, there's no acceleration, but unaccelerated methods are optimal in that case. So let me talk about the lower bounds that we obtained when we have a qth order oracle. So in contrast with our algorithms that call this oracle undeterministic and make one single call per iteration and work in any norm. So if we wanted to do something better, even if we had a local oracle that returns all of the derivatives of our function, even if we use randomization or allow for poly D parallel queries per iteration, then our lower bound would only decrease by a logarithmic factor. So we are optimal in that strong sense. So this also works for any norm, but the lower bound depends on some quantities of the norm. For p norms, we can compute that explicitly, and we show that we're optimal there. So in the case that we use a ball optimization oracle, so we use an inexact version of that, and the number of queries that we need matches a lower bound in this paper, Adele et al., that used an exact ball oracle. So let me say that part of the upper bounds, so lower bounds are completely different, but part of the upper bounds came out in a concurrent and independent work, which is this one, Adele et al. But regarding the lower bounds, actually, we simplified quite a bit all previous approaches. So previously, for non-Euclidean norms, the case p less than 2 greater than 2, they were treated very differently, and the case p less than 2 used very complicated techniques. Now we unified everything. As a result, we could solve some open problems even in the first order parallel convex optimization. Okay, let me flash a few of the ideas of the upper and the lower bounds. The word segment is quite technical, but I hope I can give an idea of how this works. So for that, we're going to start just giving a bit of intuition about what happens in the first order smooth unconstrained settings, so the simplest of all. So we know gradient descent achieves some rate, and Nesterov accelerating gradient descent improves by a square root. And the intuition behind that analysis is that you can run an only learning algorithm like Mérieux descent on the linear losses given or induced by the gradients that you compute. And in each iteration, you will get an instantaneous regret that is a sum of potentials that is going to telescope, but then something else that depends on the gradient. Particularly in this unconstrained case, it's going to be proportional to the gradient norm squared. However, we know that gradient descent also is able to descend the function by a term that's proportional to this amount as well. And so one thing can compensate the other. So ultimately, the algorithm is going to couple the predictions of gradient descent, Mérieux descent in order to obtain this improvement. So the idea behind Monteiro spider acceleration is similar. We are going to compute instead an inexact proximal point method that's going to substitute this gradient descent and allows us to decrease the function. But at that point that we find, we compute a gradient, and we use those gradients also for some online learning algorithm. So some of the ideas that we had to put into this in order to generalize it for non-Euclidean norms was using an approximate version of this non-Euclidean Moreau envelope where this norm can be arbitrary. So this is a non-standard Moreau envelope. Usually people would have used a Bregman divergence there for some other reasons, but in this case in particular, if we have this object, we show that one step of the proximal point of the operator that would take you to the minimizer of this problem, even though the Moreau envelope is not smooth, is going to guarantee descent of something proportional to a power of a norm of how much you moved. And at the same time, any subgradient of the Moreau envelope, so the Moreau envelope doesn't even have to be differentiable, but any subgradient norm is going to have a similar looking norm, which is going to play out as well in this compensation of how much the regret is versus how much we can decrease. So instead of solving this, actually, we substitute the function f by its first order Taylor approximation, so the qth order Taylor approximation in the qth most case. And so what we require for the oracle is that we find a critical point of this problem. We show that this always exists, but on top of that, if the square norm is strongly convex with respect to itself, then we can show that this subproblem is actually convex. Within the analysis, we have to make use of this new notion that we call inexact uniform convexity. So this without the delta would be just plain uniform convexity. You can run Mérieux descent on that and get a specific kind of regret. But for technical reasons, we have to allow for some error, and we show examples of regular assays that satisfy this property, and in particular, that allows us to achieve the optimal rates by using this. Okay, so then in terms of lower bounds, basically the idea is that because we know very well how lower bounds work in the Lipschitz convex case, we are going to try to lift them, which is like a general direction people have explored in the past. We are going to lift them by smoothing these hard functions, by building something then that satisfies our assumptions and transfers the hardness. In order to do this, we had to develop two main techniques to get smooth functions with respect to any norm. So one of them is randomized smoothing, where here we would substitute G Lipschitz function with respect to an arbitrary norm by another function that at each point has a value which is the average of the neighborhood center at that point with respect to that arbitrary non-Euclidean norm that we started with. So we can show that this preserves Lipschitzness is going to have some Lipschitz gradients that whose constant, the constant of this Lipschitzness is going to depend on the dimension, but this does not matter for the lower bound, so the dimension will not appear in the end. And this smoothing is also close to F. So in this picture, I have an example where I smooth the L1 norm with respect to itself, and you can see it looks very much like the L1 norm, but in the corners where you would have no differentiability, it's slightly smoothed out, and then in the center, it's almost like a sphere. And then another technique for smoothing is using some version of softmax. So we show that if you compose softmax with a linear map that is one Lipschitz with respect to your non-Euclidean norm, then this is going to have all derivatives being smooth with respect to a parameter that rescales the softmax. So then, by combining this kind of smoothings in a technical way, then we can transfer that hardness and get the optimality, even in the stochastic parallel case that I mentioned. Okay, so that's about it. Thank you very much.
Any questions?
Thank you for the talk. I was wondering, for your algorithm, you need to know like you have some Holder contingency, but you need to know the power of the cube.
Yes, like we are trying to optimize a function that has Q's Lipschitz derivative.
So you know in advance.
Yeah, in advance we know this, and then we build a Taylor approximation, right? Because we have to have access to this oracle.
And do you think that you can adapt in some sense? Like you know that there is a Q, but you don't know which one.
Yeah, I believe this is possible. So in the Euclidean sense, there have been already some works that implement the ball optimization oracle using first-order methods, or even the third-order oracle using only Hessians. I think they still need to know that there is some Lipschitzness of the higher order, but probably this can also be lifted in some way.
Thank you.
Okay, I think we should move on to the next speaker, but let's thank the speaker first. Thank you. Next is Brian.
I'll try to connect mine if possible.
Okay. You just have to unplug the HDMI. The slides are already on there if you need to, by the way. Yeah. Brian's going to be talking on faster acceleration for steepest descent. It somewhere. Okay, it's not. All right, cool.
It's Brian Bolins, and today I'll be speaking on our work about faster acceleration for steep descent. This is joint work with my student, Sita Bai. So just to set things up, The problem setting that we will be considering, it's a very standard one. Specifically, we'll be looking at unconstrained minimization, where our function f is convex and smooth. And we'll consider a couple of different types of smoothness that I'll get into in just a minute here. We'll also, throughout, let x star denote the argmin, as is a standard notational convention. Okay? So as we've seen in other talks, and as is, again, pretty typical in convex optimization, or even optimization in general, right, we're going to consider a notion of smoothness. And a lot of times, smoothness is kind of, naturally or implicitly expressed in terms of a Euclidean norm. In fact, a lot of times, the norm, a 2 won't even be included, it'll just be the same norm on the left and right, due to the sort of self-duality of the Euclidean norm. Right, and this is just Lipschitz continuity of the gradient for some parameter L. But of course, this can be generalized, as seen in the previous talk. And specifically, we can have smoothness with respect to more general norms, where the norm is on the right and the dual norm is on the left. And in this talk, we're going to focus especially on the case where we have smoothness with respect to some p norm. Right? And again, I've denoted the p star as just the dual of p. Okay? So to provide some context, and again, a lot of these things are well known, but I want to sort of set the stage and kind of give the full picture here. If we assume convexity and Euclidean, or L2 smoothness, right, then the classical accelerated gradient descent, or AGD of Nesterov, will converge at a rate after t iterations of L, our smoothness parameter, times kind of the diameter of the problem. You can also think of this as just the norm of x star if you were to initialize at 0, right? And I want to emphasize, right, that the diameter term is expressed in the L2 norm squared divided by t squared, right? So we get this accelerated rate of this t squared rather than just a 1 over t type of rate if we did unaccelerated gradient descent. Now, if instead we considered convexity along with, paired with LP smoothness, right, then a variant of AGD by Nemirovsky and Nesterov, and there are also other ways to view it in more recent works, right, will converge at a rate of the LP smoothness parameter L times the P norm for the diameter term squared divided by T raised to the P plus 2 over P, right? And so what we observe here is a certain trade-off between the norm used to measure the diameter of the problem and the rate of acceleration that we get, right? So if P were to go to infinity, you could have problems, say, something over a box, where the infinity norm of the diameter could be much better than, say, the L2 norm. But it comes at a cost, right? Specifically, you would lose the nice squared accelerated rate from having things be Euclidean, and instead, as p goes to infinity, you would get just t to the 1 power, which is actually basically is what happens if you just were to run an unaccelerated steepest descent, that is the descent method in our p norm, or the infinity norm, in the case of p being infinity, okay? And I should note that, right, these rates are known to be optimal for their respective settings. So this rate is in general optimal, but there's a sense in which it can kind of be improved for some specific problems. And I'm hiding some of the details here. I'm happy to talk about them offline, but if we consider problems such as L infinity regression, or say like the box simplex games, as mentioned in the previous talk, there are several works that have, in a sense, used the right version of an improved acceleration. Works such as the area convexity of Sherman, the work by Sidford and Tan, Cohen and al. With the relative Lipschitzness, right, that have overcome sort of a fundamental dimension dependence barrier here. Basically, what you would really love to have for this problem, the ideal case would be a general result that says you can get dimension or diameter dependence in infinity norm and a t squared acceleration. Of course, the lower bound say we can't get that in general, but we can basically get the effects of that specifically for some special cases by using additional primal dual structure in essence, right? Now, in this work, we show an alternative way that we may also, by which we may also circumvent this barrier for LP smooth problems in certain instances. So we're not breaking a lower bound, because we shouldn't expect to do that. But what we're saying is for more general cross-fit problems, we're providing a more nuanced answer. So we can't give the full improved rate that these types of results can for the special case. Rather, we give a more nuanced or muted improvement for a broader class of problems, okay? Now, specifically, right, what we do is we present a new accelerated first order method, HASD. We'll see the details of the algorithm in just a minute. And the guarantees of the method are that we can get convergent rate of smoothness times Euclidean norm squared divided by t squared times this extra g squared term, okay? So this is some sort of trajectory dependent geometry based or sort of ratio of these gradients, right? It's defined over here, but what we should note, right, the key thing to point out is that because we're depending on the ratio of the p star norm or the 2 norm, right, this can be as big as d to the half minus 1 over p, so that when we square it, the improvement in the rate, right, can improve by a factor of up to d to the 1 minus 2 over p, right? And this is, again, we shouldn't hope to or expect to get that kind of improvement to be able to say always that we can get to d to some power improvement, because that would, again, break the lower bound, right? So we need to have some type of improvement that can, that adjusts for the geometry and that doesn't immediately break known lower bounds. Another way to think about this type of result is that it provides some additional insight into analyzing smooth convex optimization for non-standard settings. That is, settings where the norm in which we measure the smoothness doesn't match the norm of the body over which we're optimizing, right? So in this case, we're considering LP smoothness with a geometry dependence in an L2 norm. And interestingly, this sort of partially addresses an open problem of Guzman from Colts 2015. Now, we can think of acceleration in the Euclidean sense as a sort of momentum, right? So we have some update being maintained, and the sort of momentum step is kind of pushing in some Euclidean direction, and we really you can think of it as some vector that's getting added, right? But a more general view of acceleration, the one that I have actually come to prefer and that was mentioned in the previous talk, is actually a view of acceleration as a sort of primal dual coupling, right? Taking advantage of both a gradient descent, or maybe more generally a steep descent step, coupled with, from a primal view, coupled with a mirror descent step from a dual view, right? So you can see that in things like linear coupling from Alan G. and Orecchia, right? So we have a primal steep descent update here, a dual mirror descent update here, where the Bregman is defined down here for some DGF phi, and then for the updated x iterates, we couple the two, okay? So our method takes a similar type of view, though we are based more, thank you, we're based more on a dual average view instead of a mirror descent view, but the spirit is still the same. The key difference from all of these others is this implicit dependence between some rho parameter related to the ratio of the norms, which induces some different coupling parameter tau between sort of the xt and the vt. All of this is to say that we have some extra mechanism for acceleration that looks very similar to that of Montero-Sveiter acceleration, for those that are familiar with this, though there are a couple of key differences. Specifically, when we have this implicit relation between xt, rho t, and the sort of implicit update, right? Whereas something similar appears in Montero-Sveiter acceleration, right? The key difference is that rather than adjusting for a difference in the power of the norm because of how the rho relates to what it is supposed to depend on, right? Here we're accounting for discrepancy in the norm itself, right? So we're accounting for discrepancy between the 2 norm and the p star norm. And we also develop a line search procedure, as in other previous works, though with some additional technical modifications, to find such a pair with some additional log overhead. We provide some natural extensions, such as if we have additional L2 strong convexity, then we can get a linear convergence rate, and if we want to find for a gradient norm minimization task, we can minimize the gradient norm in the dual norm, in the p star norm, after so many iterations as given here. But the key takeaway is a new accelerated method for LP smooth convex optimization that's based on an implicit primal dual interpolation scheme. And that kind of, again, is drawing on some of these recent techniques for high order optimization and showing how the spirit behind them can also give us new insights into first order acceleration, right? Even for first order settings can have an advantage. Some interesting follow-up works might be to ask questions about extending to stochastic or non-convex settings. And I think it would also be very interesting to consider how these techniques might give better rates for more general LP, LQ non-standard settings. And for more on that, I would refer interested listeners to the open problem of Guzman. Thank you.
All right, time for questions. Okay, maybe a quick one. Any ideas about extending this to maybe higher order acceleration, perhaps? Or?
Yes. So there's a natural extension of just kind of for, like, as you were to increase the power, you could do, I suspect, both a acceleration, like a component in relating to norms and a component of like Montero-Schweizer. So I think this would naturally combine with Montero-Schweizer acceleration, but I think even in the first order case, given that this LP, LQ, there seem to be some problems there, I think even there it would be difficult to address. So.
Cool.
Thank you for the talk. So do you think the norm can be made adaptive in the sense that you estimate the norm and it automatically adapt to the best norm possible?
That's a good question. Adaptive schemes, I suspect could be done, but it would require some work, and it would be really interesting, especially if one were to take a more practical perspective, right? Assuming that there are problems for which the natural geometry in which you should measure ellipticity isn't static, but rather is dynamic over the course of, say, training a neural net, right? I think that would be really interesting. Yeah.
All right, cool. Thank you. Let's thank Brian. Okay, cool. All right. The next talk is actually being presented by Zach on behalf of the authors, and it's on the advantage of AdaGrad over SGD. So, yeah. Let's see. Okay. Is it here? Is what? Okay. Need a minute. Let's see. Can be. Just need a technical difficulty. You need to find the presentation. So once we have that. HDMI. Yeah, just put it on top, I guess. Okay.
Okay, so I'm presenting this work on behalf of Roychen, Divani, and Aryan, who couldn't make it, unfortunately, to the conference. And this work is about the advantage of AdaGrad over SGD in the non-convex case. So recently, there has been, at least empirically, adaptive gradient methods have been doing much better than standard SGD. So you have adaptive methods like AdaGrad, RMS Prop, Adam, and so on. And it is somewhat of a mystery why they do much better than SGD. And so this is what this talk is trying to address. So the typical setting is that you have some function f that you're trying to minimize, at least in the convex case, and what you observe is stochastic gradients of this function f. So for example, SGD would have updates of this form, where the update is a function of the gradient that you observe. Adagrad norm would be similar, except that the learning rate is adaptive, and it's a function of the sum of the norm of the gradient squared. And you have Adagrad, which basically does the same, but coordinate-wise. So the advantage of Adagrad over SGD is actually well understood in the convex case. So in the setting where your feasible set is a hypercube, then basically the regret bound of Adagrad can be shown to be square root d better than SGD. And by standard online to batch conversion, this benefits can transfer to the stochastic setting. Okay, now what about the non-convex case? Well, this is much less understood. So in the non-convex case, typically you're after some stationary point, so you want to find some w hat such that the gradient of the function is less than epsilon. And the typical assumption that you make in the setting is a Lipschitz assumption, and that the gradients are unbiased and they have a certain variance sigma square. So in this setting, we know what the rate is for SGD. So it scales with 1 over epsilon to the 4 times the noise, and then 1 over epsilon square. The hope was like, okay, maybe Adagrad does better, but this turns out not to be the case. Actually, it has been shown that the rate of Adagrad norm matches that of SGD up to some logarithmic factors. And the current analysis of Adagrad, RMS proper, and Adam, they also achieve a similar rate, but then there's an explicit dimension on the dimension, which is suboptimal relative to SGD. Okay, so maybe we're missing something. One thing that we can think of is maybe because Adagrad applies the updates coordinate-wise, maybe the assumptions that we are making about smoothness, maybe we should also assume them coordinate-wise. And maybe in those instances, Adagrad might do better. So here are some candidate maybe assumptions that we can make and see if Adagrad does better in this setting. So we can assume a smoothness coordinate-wise and also an assumption on the gradient noise in a coordinate-wise fashion. And for some notation, I'm going to introduce these vectors sigma and L. So it turns out that even if you make these coordinate-wise assumptions for smoothness and the noise of the gradient, this is not enough to show that Adagrad does better. So actually, it can be shown that SGD finds a stationary point in this setting with this rate here on red. And there's actually a lower bound that matches this for a deterministic example. So there's no hope for Adagrad to do better. And so, yeah, and the worst case setting for this is actually just a 1D example. So maybe we can get an advantage if we maybe change the definition of a stationary point. So the definition of a stationary point that I showed you earlier takes the 2 norm of the gradient. So maybe if we aim for the 1 norm of the gradient instead, that maybe Adagrad does better there. And actually, this paper shows that if you aim for that, then there's instances where the rate of Adagrad is better than that of SGD by a factor of D. And actually, this was not the first time that people have considered the L1 norm. Some previous work have also considered that. Unfortunately, the rates that they get is at most that of SGD, so they didn't necessarily do better than SGD. So the main, one of the main results of this paper is this new rate for Adagrad. And it almost matches, they've also provided the lower bound, which is almost matching the upper bound. So now we're going to see how does this rate compare to that of Adagrad in this setting. To SGD, yeah. Right, so to facilitate this comparison, I'm just going to introduce some notation. So I'm going to introduce this phi sub sigma and phi sub L, which, without going into details, you can think about them as a measure of sparsity of these vectors. And also introduce this parameter R, which measures some sort of cosine similarity between this sigma and vector and L. So introducing them is just going to make it easier for us to compare the two bounds, the two rates between SGD and Adagrad. So if we look at the rates side by side, we can see that they look much more similar now, and we have this phi of L and phi sigma and so on. So you can see that the first term on SGD, we know that phi L is between 1 over d and 1. So even in the best case, the 1 over epsilon rate is going to be the same as at Adagrad. Right? So Adagrad does better, at least for that first term, even in the best case for SGD. But actually, these bounds give us an opportunity to make, to maybe cook up an instance where Adagrad would do at least d times better. So this instance is where the phi sub L vector is sparse, the phi sigma is sparse, and the sigma vector and the L vector are also aligned. And it also requires assuming that the noise is smaller than square root of L. So if all of these are satisfied, then the rate of Adagrad is better than SGD by a factor of d. How much time do I have left? Okay. So quickly, I want to sketch out the proof sketch for the lower bound for Adagrad. So the construction involves a function that is a sum over 1D functions, fi. And so let's focus on the construction of one of these functions, fi. So the construction goes as follows. We want to construct an f such that the gradient of this f takes a value 0 with a certain probability and a non-zero value for in the remaining case. And you can verify that the expectation of this gradient is just epsilon, and the variance is sigma square. And so under this construction, and given the updates of Adagrad, you can actually, there's a closed form solution for these updates. So Wt plus 1 equal Wt minus this 1 over the number of times Gt was non-zero. And so basically the points visited by Adagrad will be in this discrete set. So we know in advance what they're going to be. And this gives us some flexibility to design a function f by sort of like, constraining what the values of the gradients of this function f on these points. And so actually that's what they do in the lower bound. They show that you can pick t suitably large and force the gradient of f to be equal to epsilon or minus epsilon on these points. And so yeah, that's kind of like the proof strategy. And this is done for each coordinate separately. And yeah, I'm happy to take any questions.
Time for some questions. Maybe I'll ask, I don't know. I don't know if you have, if the authors have thought of extending the analysis to things like RMS prop or Adam or something like that.
I'm not aware.
I don't know. I'm just maybe an unfair question. But yeah, I don't know if there's anything else. All right. Well, let's thank Zach and all the authors of this paper. Last talk of this session. French keyboard versus English. Okay, we have got this. Which one is yours? Okay. All right, there's next talk is on lower bounds for non-convex optimization by Mehdi Saad.
Thank you. Hello, everyone. My talk is about some new lower bounds for stochastic non-convex optimization through divergence decomposition, which is a joint work with Wei Cheng Li and Francisco Rabona. So let me start with the general framework for stochastic optimization. So we have a function f that we will assume it's smooth and differentiable. It's differentiable over some set curved x that is convex or compact of RD. We will consider the iterative optimization methods, meaning that we have t rounds, and in each round, the learner queries the gradient on some point and receives the stochastic gradient. So this in this framework, it is well known that stochastic gradient method is the standard that powers most of the applications. And depending on the class of functions that is considered, we can develop upper bounds on the convergence rates of the SGD or its variance. So as we saw yesterday, the problem for convex functions is kind of well understood, and now the attention has shifted towards non-convex problems. And for the lower bound side, there are two main lines of work. There is the first line of work that assumes that the function is smooth, and the objective is to find a stationary point. So there are some lower bounds that are developed by Argivani in this setting. And there is the other line of work that makes some assumption on the non-convexity of the functions, which is also known as structured non-convex classes. So this includes some classes like quasi-convexity, functions that satisfy the restricted second inequality, PL condition, error bound, and so on. So I will give in the next slide some rigorous definition of those, some of those classes that we consider here. But I want to mention that in the deterministic setting, most of those classes are already well studied, so we know what is the optimal complexity for the optimization in the deterministic setting. But here we are motivated by the stochastic case. So here we focus on the following classes of functions. So we denote by X star the set of global minimizers. And we define the class of tau quasi-convex by the class of functions that satisfies this first inequality. So observe that if tau is equal to 1, this corresponds to the star convex functions. And as tau goes to 0, we allow more non-convexity for the functions. The other two conditions are quadratic growth, that typically says that the function is lower bounded by something that looks like a quadratic. And the RSI condition is it lower bounds the scalar product between the gradient and x by some quadratic-like function. So there are some works that study the relationship between all those classes of functions and some other classes. We can mention, for example, Karim et al. And Guy Escuré for a more developed comparison of the classes. So before stating the results, I will stress here the exact setting that is considered. So the function f is supposed to be smooth. So gradients are Lipschitz. As I said earlier, we query a point, we query the gradients at some point, and we receive a stochastic feedback that is an unbiased estimate of the gradient. And also we assume that the variance is bounded by sigma square. So we consider that we have t total number of queries, and we want to study what is the suboptimality gap, meaning the difference between the value function at the output and the minimum of the function. So one of the ways to characterize the complexity of the problem is to consider the minimax risk, which is sort of the best worst case error over all algorithms. And the standard recipe to develop bounds on this minimax risk is to first build some finite set of functions that are difficult, then to reduce the optimization problem to a detection one. Why this is useful is because we have this lower bound on the minimax risk to this detection problem, which is basically the product between delta, which is the cost that we incur if we miss the detection problem, times the minimax risk of the detection. So if we want to have some optimal lower bound, we need to maximize this product. And to do this, we need to take care of a delicate trade-off between two aspects. So first, we need to consider functions that are far enough so that if we miss the detection, we will incur a large loss. And from the other side, we need to have functions that are close enough in order to make the detection problem difficult, to have this probability of failure that is large enough. So to do this, we have full control on delta because we choose the functions that we construct. But for the detection part, we can use one of the standard inequalities like Pinsker, for example, to relate this quantity to a sort of average between the KL distributions. So given that the main difficulty here is just to find some functions that work, that will treat this trade-off. But I want to stress something that is particular to this problem, which is the non-convex class of functions. To illustrate this, I will give a very simple toy example. So we have here two functions. The red one is convex, so this is the derivative of the function, and the blue one is non-convex. So here the global minimizer is 0, so we can see that we have large curvature around the global minimizer. This is because we want to have a large error if we miss the target. But in the convex case, we cannot afford to have small gradients away from this global minimizer because we cannot go down. The derivative should be monotonic. While in the non-convex case, we have more freedom. We have this additional degree of freedom that we can make the derivative to be very close to 0 away from the global minimizers. And this helps because if we plot here the KL divergence when we compare the function to 0, we see that in the non-convex case, the KL is very localized around the global minimum, which makes the detection problem much harder than in the convex case. So we leverage, in order to leverage this, we need some sharp bound on the KL divergence, one that is sharper than the one that is classically used for convex functions. And luckily for us, there is in bandit theory a very standard result for lower bounds that is called divergence decomposition, which typically says that we can decompose the KL between distributions depending on how much we query points in each region of the space. So we leverage this and we construct some functions that have some local kind of curvature around the global minimum and use the previous display in order to develop our lower bounds. So to summarize, these are the lower bounds. So for quasar functions, we have this lower bound that matches almost an upper bound up to a logarithmic factor that exists in literature. This is the lower bound for the quasi-convex plus quadratic growth. So we can see that we have here fast rates. And it's also sharp because we have a matching upper bound up to the factor in black. And finally, for the RSI function, we have this lower bound that also matches the upper bound up to the logarithmic factor, and it's a lower bound that shows the role of the condition number in this case. So one last thing that I want to mention about the role of the dimension. So if you see these results, we always assume that the dimension is larger than some threshold that is logarithmic on the number of parameters. And this is not something that is due to our analysis. This is something that is intrinsic to the non-convexity, because we show that in the one-dimensional case, we can do better than those lower bounds by adapting some sort of dichotomy algorithm. So we know that we need the dimension to be large enough in order to make the detection problem more difficult and have those lower bounds. So thank you very much. That's.
Any questions before we wrap up for the day? All right, I think we are all set then. Thank you so much. Let's thank all the speakers in this session. And we have a couple announcements.
Yeah.
One of you go first.
So for those who have registered, it's time for Women in ML. So we will be going together, so please follow me.
Okay, and just one quick announcement also before following Roman. So this afternoon for the activities, hello? Okay, yeah, this afternoon for the activities we have to meet at the meeting point, and the meeting point is in front of the museum. It's written on your ticket if you are attending the museum visit, or at downtown. And the meeting point is also written on your ticket, so you are expected to be at 2:30 at the meeting point, okay? In front of the museum or downtown. I think you need 20-25 minutes to reach downtown, so you have to leave from here at around 2 p.m. Okay.